Hi, a few people have been curious about why we use all pass filters on the target responses. So right here, right? So why would you do that? And it's very simple to understand. If you narrow it down to just two interactions, it's the easiest way to demonstrate the concept of why. So um, what I'll do is reset all the targets, okay, and then we're just gonna uncheck them all, and let's use just number 3 and number 4. And the reason we'll use 3 and 4 is because those are mid-base and sub, and they're already labeled, so I'll just use those labels. So it's pretty easy to demonstrate with a mid-base and a sub. So what we'll do is we'll uncheck the subwoofer target, and we'll apply the low-pass filter, right? And we'll run it down to somewhere around, like, I don't know, let's call it 90 hertz. Okay, so now because we've changed this from a flat line, we've low pass filtered it. It has a phase shift that you would expect from that sort of a filter, a Linkwitz-Riley 24 dB per octave. So you get this characteristic phase shift. Okay, so if I high pass number 3 right here, and I make it a complementary symmetrical 24 dB high pass, then I get the same exact effect on phase, right? The same phase shift. So because these two phase shifts are 0 degrees relative to each other, right? There's no difference in the phase. That means that the magnitudes are just going to sum to +6. So the Linkwitz-Riley is down by 6 dB at the crossover point, so therefore it's flat through the crossover region, right? So if I sum these up, this is the sum trace right here. It sums flat, and it has the same phase shift that either one of the individual traces by themselves has, right? Okay, so that part, so far so good. Okay, so other than the phase response, the summed combination of these two low pass and high pass filters results in a perfectly flat line, right? Other than the phase response. Okay, so I could model the magnitude response, that perfectly flat line, if I wanted to, with T2 right here. And we'll just call this our compare. This will be our compare target. Okay, so we got mid-bass, subwoofer, and compare. Now compare, we're not going to sum it in. We're just going to use it as a comparison. So let's say that I took this this mid-bass, this high pass, the green one, and let's say I wanted to low pass it now. I wanted to turn it into a band pass. Okay, and I went like that. Okay, at 10K. All right, well, if I took my compare trace and I applied a 10K low pass filter, it's identical to the sum, right? It's identical to this guy. So in fact, now we're going to talk about the difference between the sum and the compare trace. Okay, they're identical at this point, totally identical. All right, so what if my bandpass, though, which is this mid-bass trace, this guy, the green one, okay, what if my bandpass trace was, instead of low passed at 10K, what if it was low passed like down here at 200, and let's call it 250? Okay, what if it was low passed at 250? Well, if those two signals are summing up properly, the sub and the mid-bass, if those are summing up properly, then just like before, they should add up to equal the same thing in the magnitude as my gray trace right here, my compare trace, right? So where were we? We were 250. So let's put a 250 low pass on this guy. Okay, well, they're not the same anymore. So let's go ahead and hide the individuals again. Okay, so, and we're looking at the bottom graph right now. Okay, we're not looking at the phase graph at the moment. We're looking down here. All right, so now what's going on? Well, my summed combination between subwoofer and mid-bass no longer add up to a single unit that's low passed at 250 hertz. They should, but they're not. Why are they not? Well, let's investigate that. So the reason they're not adding up to a single unit at 250 hertz is, let's go ahead and take our mid-bass low pass and Let's run it back up again like this. Okay, so in fact, let's take this one and let's apply a high pass on it. So we'll have a second compare trace at 90 hertz. Okay, so we're going to adjust our mid-bass trace here. And notice the phase response of the red up here. Okay, so the purple phase response, which is the subwoofer, it's not going to move. It's going to stay right where it is, right? But the green phase response, which is our mid-bass, as we run this filter down, it starts to deviate from where it used to be. Okay, the red and the purple, basically here, they are defining where that filter used to be, where that response used to be. But because we're running this as a bandpass, now the phase shift of the high-pass filter is encroaching upon, or it's starting to steepen the phase angle, where there used to only be a low-pass filter by itself, a low-pass filter's worth of phase shift by itself. Now there's a low-pass filter and a high-pass filter's worth of phase shift in this general region. So as you can see, the green trace now has deviated from where it used to be. Now it's 90 degrees down from where it used to be, right? So we need to make the subwoofer also have 90 degrees of extra phase shift so that they'll sum up like they used to, right? So they'll sum up to a single trace that looks like this gray one here, right? So again, this gray one is low passed at 250. So let's take our mid bass and let's run it from 90 hertz to 250 hertz. Okay, and together, as you can see, this green and that purple should add up to that gray, but they don't. They add up to that yellow right there. Okay, so what we need to do then is we need to take this subwoofer trace, and because we created extra phase shift on the green by using a low pass, we're going to take this subwoofer trace right here and we're going to create extra phase shift on it by using an all pass. So we'll take an all pass and we'll just roll it down on the subwoofer. Okay, now we're looking at the top graph. We're going to roll it down on the subwoofer until it overlays the green. There. Okay, now when these two add together, they're going to sum up to be exactly like that gray trace right there. So let's see what happens. Okay, now there's the sum, and if we compare it to our just a single low pass 250 hertz, it's identical in the magnitude. I'm looking at the bottom graph again now. Sorry. Top, bottom, top, bottom. Anyway, so that's it. That's why. It's just simply because if you move this here, let's turn the all pass off now. Okay. So as I bandpass this green trace here, and my low pass filter right here starts to encroach into the area where the high pass filter used to exist in isolation. Now it's no longer existing in isolation. Now the low pass and the high pass are both right close, right next to each other. Then as you can watch the phase shift in real time up here, you can watch it shift downward, right? So right now those two things, the green and the purple, sum up perfectly. They sum up to this yellow trace, right? And as this frequency gets lower, they stop summing up perfectly. And why is that? Well, the only thing that's changing, the only reason why they're no longer summing perfectly is because of added phase shift in the green. So to compensate, you would add phase shift to the purple, to the sub, just like that. Now they sum exactly right. So so now we're low passed at 315. So if we took our compare trace and put it to 315, now they're identical. Now the compare trace and the sum trace on the bottom graph again are identical. See? So that's why.